want to explain equality of masses of proton and neutron, and if you want to explain the same interactions of protons and neutrons, you can try with just without minus 1, 1 and 1. At least in this respect, you can explain these things. However, there are some other consequences of wider group. We may probably discuss this in the end of the course. Now, another point is that, remember, there was a bit of confusion that we are discussing strong interactions. Nevertheless, we are introducing something which depends on electric charge. For instance, isospin. It's different for particles with different, for proton and neutron, and therefore we connected this even with electric charge. So it's kind of, now we have some symmetry with this mixture of strong interactions, and it looks like electromagnetic interaction. These things exist at hadron level. When we will go to quark level, we will see really some different disentangling of symmetries and interactions responsible for strong interactions, what we see as strong interactions, and electromagnetic interactions. Another thing I want to add is we can extract lesson from isospin, because further this type of the symmetries will be enlarged more and more once new particles are discovered. And so what we learn, so isospin symmetry is SU2, so we started from the simplest version permutation, but then it can be extended to SU2, and then different consequences of this SU2 isospin have been confirmed. So there are some relations between the different processes, and that confirms SU2 as a symmetry of the isospin. So what this symmetry allows us to do? Classification of particles, right? So we now know that proton and neutron have this isospin plus 1/2 and minus 1/2, and so we have kind of new quantum number. This new quantum number corresponds to generator of the group which is diagonal. So this is important. If you have the group transformation symmetry group, and you have diagonal generators, you can identify these generators with some physical quantities which produce for you quantum numbers. And these quantum numbers can be used for classification of particles. So let me probably even write it, because this is an important thing which will be repeated several times. So we have this isospin group which has diagonal generator. So more precise is 1/2 sigma 3, and it can be identified, it corresponds to physical quantity. To physical quantity. So isospin, this is what we call isospin, or third projection of isospin. And that allows us to classify particles. So, this is what I already mentioned before. It's amazing that formalism of group theory has been developed much before particle physics has been developed. And still we see that the theory, or the theoretical construction, reflects well some properties of the real world. And this kind of identification is very non-trivial. So why we have this mathematical formalism, and then we find in real nature something which kind of can be identified. Some items of your formalism or mathematical formalism can be identified with some real physical observations and properties of physical systems. So here diagonal operators are identified with physical quantities, which then allow us to classify particles. So we are speaking about symmetry group. And this is symmetry of interactions. So when we are saying the group and particles form doublets or triplets like pions, this means that interactions are invariant under this transformation. So not only classification, but what we are keeping in mind here is that the interactions are invariant under symmetry transformation. We will have also some exercises to check this. So it's symmetry of interactions. Formally, this means that if you are doing transformations of our fields or particles involved, then Hamiltonian, which describes interactions, is invariant. Okay? Again, let me repeat that the form of the Hamiltonian in terms of some initial fields and transformed is the same. This is what we call invariance. So let me reproduce the formula which we have obtained last lecture. This is a relation between electric charge, isospin, plus what we call hypercharge, and hypercharge equals baryon number plus strangeness. And this is Gelman-Nishijima formula. And sorry that I put this Nishijima-Okuba. There's another formula Okuba and there's another formula by Gelman and Okuba which relates the masses of the particles. So this is Gelman-Nishijima formula. And it was found in the framework of developments of the concept of strangeness. So this is a very general formula which actually allows you to connect electric charges, isospin and hypercharge, or baryon number, and strangeness of pions, proton, neutron, and also strange particles like K-mesons. So the concept of quarks appeared, as I said, from classification of hadrons. So it's like a zoo. You have many animals, so you make classifications of these animals. And what has been done is that all these particles were grouped in different families of particles. And as usual, there are some properties which are common for all the family, a given family. So what are common properties for a given family? And those are baryon number, spin, and then parity. And the parity is the property of the wave function under reflection of coordinates. So there are particles which under this reflection of coordinate have wave functions which doesn't change the sign, and these particles we call a scalar, for instance. And particles which change, whose wave functions change the sign when you do reflection of coordinates, which means z go to minus z. And then under this transformation, the wave function changes the sign. These are, for instance, pseudoscalars. So parity. Put here as spin, here is parity. So a given, all components of a given family have the same baryon number, spin, and parity. What distinguishes particles within the family. What are differences? Within the family. And those are electric charge. So within a given family, you have particles with different electric charges and strangeness. Now this is strangeness. Or you can use hypercharge. So you can use also, instead of these two, because of this relation, you can use the third projection of isospin instead of electric charge and strangeness. So or so you can use these two, or these two. And due to these relations, they are connected.
What's the mass?
The masses are different. Yeah, of course. So I mean quantum numbers, what is the masses? Yeah. So let me present examples of families. So the first family is the family with baryon number equals 0, with spin equals 0, and with parity -1. So that's the family of pseudoscalars. So particles which have this property that change the sign, the spin 0, are called pseudoscalars. So let me put these particles, and the family has 8 members. And let me put this in the plane strangeness and the third projection of isospin. 0, 1/2, 1, -1/2, -1. And for strangeness, 0, 1, and -1. So let me put it first for construction. So particles with spin 1 are K0 and K plus. Now strangeness 0 is pi minus, pi 0, and pi plus. So these two form isospin doublet. These form isospin triplet, and here what we put is K minus and K0 bar. So this is antiparticle of this K0.
We're missing one.
So what is missed is atomism, which is sitting here. It has 0 electric charge and 0 strangeness. So this family is the family of particles with spin 0 and parity -1. You can find in particle data group this type of notation for members of this family. And we can connect these particles positions, getting this nice plot. So this is object of methods. So let me give you another example for baryons. So now we deal with family which has baryon number +1. And there is another family with baryon number -1. And with spin 1/2, and for fermions we are not introducing the parity. So the strangeness 0, -1, and -2. And of course there is a symmetry when you go to family of antiparticles. You will have here +2, +1, and 0. Okay? Sorry?
What's the difference between eta and pi0?
Oh, they have different. We will see. So these particles have hidden strangeness. So we will describe this.
And where is the
And mass, of course. So what has been found is family, and isospin is 0. So they are sitting here. You see, pi0 has still total isospin 1. So they form isospin triplet with pi minus and pi plus. This guy is separate because it has isospin 0. So let me put it. Eta has total isospin 0, and it has the self projection, of course, 0. Instead, pi 0 has total isospin 1, but the self projection is 0.
Single.
And of course, it is singlet of isospin group.
What is the parity of this family?
Sorry?
The parity in this case.
Parity. So what I'm saying for fermions, these are particles with spin 1/2. There is no sense to introduce parity.
I see.
Okay, so let me put here 0, 1/2, 1, -1/2, -1. So here on the top we have neutron and proton. They have strangeness 0, and they form isospin doublet. In the next line, we have sigma minus hyperon, sigma 0, and sigma plus. And then the down, we have theta 0 minus, and here's theta plus hyper, it's the 0. And here another component is lambda, which is singlet, isospin singlet, in the same way as eta. So these sigmas form triplet. And then again they connect and get this nice picture. So this is again octet of baryons with spin 1/2. And we have similar octet for anti-particles, anti-neutron, anti-proton, everything like this, but you need to particles. Yeah?
Again, why didn't we introduce that parity?
So we do not introduce parity for fermions. Because, and I will discuss this later because it will be a lecture on the parity. Because there is no physical consequences. You can still introduce such transformations, but they have no physical consequences, in contrast to this parity for particles with spin 0, and also we introduce parity with spin 1. So, and also the point is that fermions always appear in pairs. So then this parity, why it doesn't have a sense. Right? So you can introduce parity, but then it doesn't produce any kind of physical consequences. In contrast to bosons, because boson can be produced as a single particle, for instance, right? And you can have fermion, and boson. And so this is why the parity has sense. So sometimes it forbids some processes. This is not the case for fermions. More questions?
Just to make sure, if I have a system of neutrons and protons, what this idea of ion-scanning says that if I exchange the protons with neutrons, the strong interactions will be the same.
Yeah.
But it doesn't say that if I replace one neutron in the system with proton, that this is not a symmetry, right?
No, it will also have the same interactions. Like for instance, remember we discussed mirror nuclei. Tritium has one proton and two neutrons. And helium-3 has one neutron but two protons. So, and we here substitute just one proton by one neutron. There are also other systems of this mirror nuclei. So you can interchange any number of protons and neutrons within the systems, and you will get still the same interaction.
But if I have a bound state of neutron and proton, like neutron, if I exchange this neutron with proton, it will be two protons together, but they do not form a bound state.
Yeah, because strong interactions will be the same. However, the strong interactions are too weak to keep the system, because you have strong repulsion.
So the strong interactions are the same, but it's forbidden because of electromagnetic.
It doesn't form a stable composite state. Okay. So this type of classification led to the concept of so-called eightfold wave. So what is that? What's that here? And Gell-Mann was one of the guys who developed these ideas. So the idea is that these families of 8 particles form multiplets. So octets. They form octets which transform under representation eight of some symmetry group GF. Now we call this group family groups. Some symmetry group. GF is the symmetry group of strong interactions. And here I can repeat the story, the same story with, as we had with isospin. So in the same sense as SU2, isospin is the symmetry of strong interactions. Here there is a bigger group, or some new group, GF, which is the symmetry of strong interaction. What does it mean? Now we have these octets. Well, let me denote this octet like M. So this is octet. And it is transformed under representation of this group J. So V is representation of the symmetry group. And this is 8 by 8 matrix, right? So it's 8 by 8 matrix, which gives you transformation of initial fields to this transform. Under this transformation, what's going on? Says out of these 8 components, when you do this transformation, you get some interchanges of these particles or some combinations. So you will get 8 combinations of these initial particles. So then we say that our Hamiltonian, which is functional of octet and maybe some other fields, can be written in terms of these transformed fields. And so I'm writing here V, G, mod M. So this is just identical transformation. So instead of M, according to this relation, I have Hamiltonian in terms of M prime. If we show that this is reduced to the same form, but in terms of M prime, this means symmetry. Symmetry of the Hamiltonian with respect to transformations Vj. So then J is the symmetry of this Hamiltonian. We are saying that Hamiltonian is invariant with respect to Vg transformation. And so G is the symmetry of this Hamiltonian if we have this invariance for all elements of the group. Okay? Like in the case of ISP. Now, what is this group GF in this case? Can it be SU2? Suppose SU2 has representation A. SU2 has represent all representation 2, 3, 4, 5, 6, 8. Can it be? The answer is no, because if you have representation, take representation of 8, then we have here particles which differ by electric charge by 1 unit, like in the case of proton and neutron. But now you will, or pions, we have pi plus, pi 0, pi minus. So the charge changes by 1 unit. So that you will have here, say, Q, yes, Q minus 1, Q minus 2, Q minus 3, Q minus 8. But this is not what is staying in our families, what we have shown. So at most you have double charge, or you have just single charge particles, plus, minus, or 0, right? So SU2 doesn't work. There's another important feature of our families, that actually we have 2 quantum numbers, not just one, which classify these particles, right? So we have I3 and strangeness. To have this kind of correspondence of group symmetry formalism and real observations, we need to have the group which has 2 diagonal generators, which we would then assign to these physical quantities. Okay? So one is to have the group with 2 diagonal generators. Which then will serve as operators of the corresponding physical quantities. So now we see we are establishing relation between formalism, what I'm doing, and physical observations. So we need to have this group, and we also want to have isospin within this group, right? So that our SU2 isospin should be embedded also in this GF. And of course, the minimal step is clear that we need to consider group SU3, which satisfies all these features. Right? So it has a subgroup SU2, and therefore we can describe isospin, and particles in our multiplets have different isospins, so isospin should be included. And it has two generators. Now, the group SU3 has a fundamental representation 3, and it also has a complex. This complex group, and therefore it has 3-bar complex representation. So we can construct the high representations by multiplying this. So 3 times 3-bar is a reducible one, and in terms of irreducible representations, it can be expanded as 8 plus 1. Okay? So we also can consider 3 times 3 times 3, product of 3 fundamental representations. So here we get 27 elements, here we have 9, here is 27, which can be expanded into irreducible representations, 10 plus 8 plus 8 and plus 1. We also can consider 3 times 3. Without this conjugate, actually here there is no also conjugate. So that equals 3 plus 6. Right? So you had this in your group theory course. Now the idea of this eightfold way is that octets form irreducible representations of SU3 symmetry group. So to say, octets are transformed under representation 8 of SU3 symmetry group. Again, what is the meaning? This means that Hamiltonian of strong interactions is invariant under these transformations. This is one aspect, and another one, the SU3 gives for us classification of particles within the multiplets. The role of the group is this twofold. It gives classification. It also implies that the masses, all the masses of particles in a given family should be the same, which is not true, right? So you know that K meson is 3 times heavier than pions, more than 3, and therefore this is not exact symmetry. So the symmetry should be broken somehow to get different masses. So everything was nice with this isospin because the particles within the multiplets have almost the same masses, with some small violation because of electromagnetic interactions. Here, violation is much stronger. Okay. So that's the meaning when we are saying that these particles form octet of SU3 symmetry group. We are not adding all these things, but the meaning is that we deal with Hamiltonian of strong interactions, And under transformations, the Hamiltonian is invariant. Okay. Now the questions are that SU3, and this is very important actually fact, which I think you should keep in mind when you discuss some present-day situation. You see there are some other representations irreducible of SU3, like 10 here, and like here, fundamental representation. And so what's going on with them? Let me just say in advance, nowadays people are constructing a lot of models with different symmetries. And sometimes, in most of the cases, they are using just some of representations, but not all representations. Say, okay, we don't know what's going on with other representations. I think this is very bad examples. So nature doesn't want to miss some, at least lowest representation. And you will see here that behind this question, where are these triplets or tenplets or sixplets? There's very important physics behind. So if some in your model representations are missed, it should be very good reason. It should be explanations. Not only you are introducing some symmetry and say, okay, we'll just use a given representation and just neglect and not to do anything with others. One should answer the question, where are other representations? Why there is no particles which are transforming under other representations? Now the answer about this one is very simple. And in fact, people have found particles which form tenplets. So one of the examples is baryon family with baryons of spin 3/2. So let me again draw the diagram. Strangeness 0, 1, isosphere 0, 1/2, 1, 3/2. Minus 1, minus 3 over 2. So this is isosphere, the third projection of isosphere. Okay. So here we have the following particles. Delta minus, delta 0, delta plus, delta plus plus. Actually, these play important role in these particles play in scattering of pions on the protons. And we will have some exercise actually where you will deal with these guys. So you see there are 4 components. They form representation 4 of isospin. There are 4 components in isospin multiplet. So next one is sigma, but this is another sigma with spin 3/2. We had already sigma before. So sigma minus, sigma 0, and sigma plus. Then theta, but it's another theta with spin 3/2, and usually how people distinguish, they put here in brackets and put 3/2 so that one can see difference between sigmas which we have discussed before. So there are a triplet of sigmas. There is doublet of theta, should be here, theta 0 and theta plus. And by the time of development of this eightfold way, only 9 components were known. So you can connect in this way. And then if you really have this SU3 symmetry, and you need to have 10 components because there's no representation 9. So then one would predict on this basis the existence of this particle, which is omega minus. Which has strangeness -3, you see. So that was prediction. From SU3 interpretation of all these families and classifications. And this particle has been discovered after. So that was very important confirmation of existence of this SU3 family symmetry. So let me have this nice triangle. And this is omega. That's omega. That was prediction and was discovered. So, fine. We know what happens with 10. 10 plates exist, so it's not only eightfold way, but now I have more complicated content of the theory. Now, how about these fundamental representations? So you see, it's important to ask questions. Why we have some theory with kind of highest representation, but there is no fundamental, there is no low. Nature doesn't like to miss lower representation. So if you have some symmetry, it should start to fill in the things from starting from the lowest. So this is experience which we have from particle physics, from history of particle physics.
Well, what about the singlet presentation?
Sorry?
What about one?
Oh, singlets, yeah. So there are singlets. Yeah. So I will discuss some. These are combinations, for instance, when we go to quark sector, I will discuss. There's some eta prime. Remember, I had this octet of mesons, and it was pi 0, and the same point is eta, but it also discovered eta prime. So that also exists. Yeah. Now let's focus on fundamental representations. And the answer to this question is you already mentioned, is the introduction of quarks, which do transform under fundamental representation.
How about pentaquarks?
Yeah, so I will mention this also later. They exist, yeah, it seems. So, quarks. So also, it answers the question, what is the meaning that we have particles which transform under this 3 times 3, for instance, or 3 times 3 times 3? What is the meaning of these transformations? So the answer, unique answer, is given by Gell-Mann, Zweig, and Neumann. By the way, George Zweig then moved to neurobiology. He didn't continue his career as a physicist. And Yuval Neumann. And what they suggested first is that the hadrons are composite systems of quarks, more fundamental objects. states of more fundamental. Objects, and Feynman has called them quarks. And so what is connection between quarks and Trieste? Yeah, so James Joyce was here and he took this term from James Joyce novel. More precisely, what Gell-Mann et al. Suggested is that the mesons are composite systems of quark and antiquark. So that the wave function of meson is the product of the wave functions of quark and antiquark. So quarks are transformed as a representation 3 of ratio 3, and antiquarks are transformed under representation 3 bar. So therefore, the wave function of meson should be transformed as 3 times 3, and this is what we need to explain, to describe the mesons. These are for mesons. Baryons are composite systems of 3 quarks. And so the wave function of baryon is the product of 3 wave functions of quarks, and therefore they are transformed as 3 times 3 times 3, and among these products we have irreducible representation 8 and representation 10 and singlets. So quite recently people discovered also the particles, so-called pentaquarks, which have composition quark, 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 antiquark. It was a big kind of deal to distinguish this system with just system of baryon, and this is meson. It looks like so you need to have some kind of subtle measurements to say that we deal with some new state of 5 quarks and not just composite state of baryon and meson. What are properties of quarks?
How was it discovered, the metaphor?
Oh, that was discovered as a resonance against its very shortly living systems, and so you have scattering of mesons and baryons, they say pi and proton, and you see properties of this, what you get in final states. And what has been found that the cross section has some resonance. It was discovered as a resonance. So properties of quarks. Quantum numbers we have introduced so far, apart from parity, are additive quantum numbers. So isospin, strangeness, electric charge, baryon number, so all they are additive quantum numbers. And using this, you can reconstruct what should be the property of quarks, knowing the properties of mesons and baryons they are made of. And we will have exercise to do this. So let me probably do the following. What does it mean? So this means that I3 of hadron equals the sum of I3 of quarks which compose a given hadron. So over E I. And I can be 2, 3, or 5. And the same is for other quantities. So the strangeness of the hadron is the sum of the strangenesses of quarks which are inside a given hadron. Well, clearly the baryon number should be 1/3. Because if you put these quarks in the triplet, which means that baryon number of each of the quarks inside the triplet should be the same, right? And therefore, baryon number of a particle which is composed out of 3 quarks should be 1, like a proton, and therefore baryon number of a quark should be 1/3, an antiquark minus 1/3. Spin, the simplest possibility is 1/2. So let me spin. So then you can explain spin properties. Of course, you can try that spin is 3/2, but again the question is why nature doesn't use 1/2. The simplest possibility is 1/2, and I think 3/2 probably is excluded experimentally. Okay. So let me see what I want to add. At this point, because you will have exercise. So let me maybe immediately introduce notation of the quarks. So we introduce this triplet and notations of quarks U, D, and S. And for instance, mesons, which are composed of these quarks U bar, D bar, can be represented in the matrix form as bar, U, D bar, and S bar. Sorry, this is result bar. Right, so here you will have state U bar, etc., and then identifying these states with known hadrons or known mesons, you can find what are charges, electric charges, spin, isospin of the quarks. That will be your exercise. But in fact, one can do this identification in more systematic way using group theory. So this is what I will show you now. So remember that SU3 has 2 diagonal operators which should correspond to physical quantities, and we can select different quantities, but we will select isospin and strangeness as we did before. And we can first try to identify operators of these diagonal generators of the group with these physical quantities. So let me write it again. We use the operators of physical quantities correspond to diagonal generators of the group. So one of the diagonal generators of the group is 1 square root of 2 lambda 3. And it has the form 1/2 minus 1/2 and 0. And so it's clear that that can be identified with I3, the third projection of isospin. So this will be the operator of the third projection of the isospin. So we had this kind of already assignment when we discussed proton and neutron. So according to this, U quark, isospin of U quark should be 1/2, and isospin of D quark should be minus 1/2, and then the isospin of S should be 0. So another diagonal generator is lambda 8. Let's take this. I think it should be under square. Lambda 8. And it has the form 1/3, 1/3, and minus 2/3. Zeros here, zeros are this diagonal. That can be decomposed into 1/3, 1, 1, 1 diagonal plus 0, 0, minus 1. And so this first part can be identified with baryon number, and this one with strangeness. So we do this identification. You can consider this as an assumption, but then you should check everything, right? So if you get correct or not, finally, charges of hadrons. And you can check this also experimentally. Even experimentally, people measure the charges of quarks eventually. By the way, in the early days, people discussed the theories where quarks have integer charges. People were kind of uneasy with these fractional charges. There were theories with the integer charges of quark, but then it was eliminated by the experiment. So this lambda 8 then can be identified with B plus S, which is nothing but this hypercharge. And so what we see from here is that, for instance, taking this part, that strangeness of U quark is 0, strangeness of D quark is 0, and strangeness of S quark is minus 1. Strangeness of S quark is minus 1. Let me give you the table of these properties of quarks. I have U, D, S, and then the third projection of isospin, strangeness, and baryon number. 1/2 minus 1/2. 0, 0, 0, minus 1, baryon number 1/3, 1/3, 1/3. And then we can construct Q using Gell-Nishijima formula once we already have this identification of generators of isospin B and S. So the electric charge is given by I3 B plus S over 2. And using this identification, we can find that electric charge of U quark should be 2/3, D quark minus 1/3, and S minus 1/3. We also can write the diagram in the plane of strangeness and isospin, which corresponds to 3 quarks. So it's very simple, because 0 minus 1, and here 1/2, and 0. And so we have D quark here, have U quark here, and S quark here. So this simple triangle. Questions? And again, let me remind that all these kind of prescriptions were eventually tested, checked. First of all, checking if you get correct quantum numbers of hadrons, and then even experimentally. And so again, there were some models where you have integer charges of quarks. That has been eventually excluded. So once we introduce quarks, now we will reformulate our theory, what we have created before, in terms of quarks. Now we go from hadrons to quark level. And first of all, we will start with the weak interactions, and let us consider how weak interactions look like at quark level. So let's start with beta decay. Beta decay is transition of neutron to proton with emission of leptonic pair. And at quark level, it would look like the following. Now we know that neutron consists of 1 U quark and 2 D quarks. So this is the composition of neutron. And you can check, so first of all, the electric charge is 0, right? So isospin is 1/2, because we have the 3 particles with isospin, and so you can get a combination which corresponds to isospin 1/2, and strangeness is 0. Proton has 2 U quarks and 1 D quark. So this is the composition of proton. Probably I should, let me put D here, sorry, and U here. So one needs to transform one of the quarks to U quark to get proton. And this is what has been done by weak interactions. So we have here electron and antineutrino emission. So in this way, we reproduce a neutron decay. So neutron decay is transformation of one of the quarks, and one needs to sum, of course, all these two possibilities, into U quark with emission of leptonic pair. So this we know that this is described by a leptonic current, which is gamma mu. We want to have alpha, that's a gamma alpha 1 minus gamma 5 neutrino. So this is what is described. And now we will write what would correspond to this transition of quarks. And at hadron level, we introduced already the current, which is proton alpha 1 minus GA gamma 5 n. And at quark level, we need to write something like U quark gamma mu. And in general, let me write here G quark V minus G axial quark gamma 5 D. So this is what we had at hadron level. And in general, in quark level, we have here different constants. Essentially, these are coupling constants, which eventually should be multiplied by G Fermi. So, but at quark level, these constants in general are different from what we have at hadron level, right? So, what are relations between, but still some relations should exist between vector couplings and axial vector couplings. So, what are these relations? And you see, this is an important step toward the standard model, the relation of the standard model. So this is the simplest what we can write for quarks, right? We need to have gamma alpha, right? Sorry. You wanted me to write alpha. Gamma alpha, this is clearly from Lorentz covariance. And we need to have transformation of D quark to U quark. And so this is in general what we can write at quark level. There are two important concepts or principles which are behind establishing relations between these couplings, and one is conservation of vector current. This refers to vector part in this quality, and that tells us that G quark vector should be equal to G vector hadron, and this should be 1. This means that strong interactions do not modify vector current and the coupling of vector current. This is at quark level. And here we are considering quarks as free particles, right? So we have this assignment for the current. But then going from this quark current to hadron, we need to take strong interactions. That quarks are not actually free, as they have strong interactions. So, in an attempt to find connections between couplings, you need to take into account strong interactions, that quarks are not free particles, but they have strong interactions. The difference of the couplings at quark level and hadron level is related to strong interactions. But you need to take into account that quarks have strong interactions. This equality means that strong interactions do not modify vector couplings. They're the same. And this actually is analogy to what we have with conservation of vector current in electrodynamics. So suppose we have quark with charge. So let me put this analogy. I will explain this using analogy with electromagnetic interactions, where also vector currents are conserved. And actually people discuss this current algebra, which is based on that you include these currents also together with electromagnetic current. And so they have common transformations and the same nature of conservation of vector current in electromagnetic interactions are here. Analogy with electromagnetic current. So suppose I have quark with a charge 2/3. This is free quark, so without inclusion of any strong interaction. Now let me go a little bit in advance, that will be simpler. I will take strong interactions in the form of interactions with gluons, which is actually what we know now. So the strong interactions are due to exchange of new particles, new gauge bosons, with the name of gluons. And so these are zero charge spin 1 particles. So when we include this in the first order, you may have the process when quark emit gluon. So we have it quark here, then the same quark with the charge 2/3, and gluon. So now we measure again the electric charge of the system of quark and gluon. Since gluon has zero charge, then the total charge of the system will be again the same, 2/3, which means that you include some interactions, but they do not change the charge. You may have even more complicated case when your quark emits gluon, then gluon is transformed into quark-antiquark pair. Again, if you measure electric charge of your system in this moment, you will get the same 2/3, right? Because this is quark-antiquark, this has zero charge, and therefore you have quark and antiquark of the same type, say U quark and anti-U quark. So the total electric charge of this system is zero. So again, the total charge of whole your system is zero. Oh, sorry, the same as in the beginning, 2/3. So in spite of very complicated interactions, and you may have much more gluons, virtually are produced, transformed into quarks, then they're absorbed, so you may have messy the cloud of this. But still electric charge is zero, so the same as it was before for bare quark. And this is because in each of these vertices you have conservation of electric charge. And therefore whatever complicated configuration you have, the electric charge of your system will be still 2/3. So this is the basis of this conservation or quality of these couplings. So this is analogy, this G is analogy of electric charge in electromagnetic interactions. So you add strong interactions of quarks, but still the total charge or total coupling of weak interactions will be the same as here and here. So it will be the same. After inclusion, you have the same coupling. Strong interactions do not modify this weak interaction coupling in the same way as strong interactions do not modify electric charge here. Okay? So this is one thing. Even more amazing is the following. So this is one, conservation of vector current. And in the case of axial vector current, we have an idea of partial conservation of axial vector current. Partial conservation of axial vector current. So remember that the GA was approximately 1, 2, 3 for neutron and for free neutron decay. This is what was in beta decay. So it deviates from 1. Not only this coupling actually differs from different hadron systems and for different nuclei. For instance, if you consider beta decay of nuclei, this G can be different. It can be even smaller than 1. This is what we call now quenching of this coupling. And people from this reactor neutrino community, they actually struggling with the understanding of this GA and its effect. So
Also depends on the energy, right?
it also depends on the energy, yeah. So you see it was 1.33, and this is effect of strong interactions. So axial vector current is affected by strong interactions, but not strongly. And then it was idea, and it was checked and proved, that actually at quark level, the situation is even simpler. So the axial vector coupling at quark level is 1, like vector coupling in these units. So which means that you start here with current U, gamma alpha, 1 minus gamma 5, D, and then this coupling is not renormalized or not changed by strong interactions, but this is modified. For neutron, it modified up to 1.23, and this is why it's partial non-conservation. So you have a deviation from 1, but it's not big deviation. At quark level, the situation is simpler, and we get this very important result that at quark level, we have V minus A structure of the current, the same as in the case of leptons. Remember, we had this lepton current, which is L, gamma alpha, 1 minus gamma 5, neutrino, L, lepton or muon. And now we have the same form of the current. And this is extremely important. Without this, you would not write the Lagrangian of the standard model. So this is so-called universality of interaction. So not only couplings are very close in all these processes, apart from mixing angle, which we have introduced, Kabiba mixing, but the form, Lorentz structure of the currents is the same. So now we can write Hamiltonian of weak interactions. And this universal form Hamiltonian equals G Fermi square root of 2 and then G alpha work multiplied by G lepton alpha plus Hermitian conjugate. And so for this quark current, maybe I should not write this again. So for quark current, I have this U gamma alpha 1 minus gamma 5 D. Probably I will finish by pi decay. So this is for beta decay. So this is the current. I can actually also write this D, indicating that I have D quark in a given current. So now let's go and consider pi decay. So how pi decay looks like at quark level. Pi minus, for instance, consists of U anti-quark and D quark. So this is the pi minus. Now this system should be transformed into mu minus and neutrino, antineutrino, mu antineutrino. Right? This we know how. And so to do this, we just need to connect these two lines. So that we have here transition of D quark or annihilation, if you want, of d quark with u anti-quark. Or in other words, transition of d quark into u quark. And you realize that this is the same current at quark level, which is responsible for beta decay, is also responsible for pion decay. It was kind of obscure current which actually annihilates pion. Remember, we introduced this hadronic current in general, which transforms pion state into vacuum state when we discuss pion decay. Now we see at quark level that what's going on is annihilation of u anti-quark and d quark. So this is what is behind disappearance of pion. And what is important, the same current as we had for beta decay is responsible for pion decay. Now, as I said already before, the total Hamiltonian of the system is actually sum of all these separate pieces we introduced for different processes. Of course, we shouldn't make a double counting. We should not introduce the same current which is responsible for pion and beta decay twice. And therefore, the total Hamiltonian, which includes pion decay and also decay of beta decays, will be GF square root of 2G. And let me put here D. Current alpha multiplied, and here I can sum up the leptonic current, the lepton current plus muon current plus Hermitian conjugate. And by the way, muon decay, we have already written again, have the same form GF square root of 2. So here I have neglected for time being this cosine deviation of cosine, because I took cosine theta equal 1 for time being. So I will introduce these corrections tomorrow, Monday. So that's for beta decay, we have alpha mu multiplied by alpha 8. So the product of these two plus Hermitian conjugate. And this is Hamiltonian, which is responsible for muon decay. So you see, everything becomes very simple and universal. So everything is in the form of products of currents, and all the currents have this V minus A nature. So that's it for today. Questions?
So the TA is close to 1 for at the part level is some experimental fact is that's how it was discovered, or
What is discovered?
that is close to 1?
Oh, for experiment, yes, it was experimentally checked because what's interesting that at high energies, we are discussing now low energy phenomena, but at high energies, you immediately test interactions with quarks. If you go to higher energies, which are bigger than, say, 1 GeV, which means that you are probing already your system at scales which are much smaller hadron scales. So going to high energy, immediately check the couplings with quarks. This is one possibility.
Still 1.
Yeah, so of course there's some kind of renormalization group effects which are small for weak interactions up to, say, MW boson rather high energies. Yeah.
And you can still write as a Hamiltonian for the strong interactions at the conditions that you are mentioning, because I had heard that on chronodynamics it's still not possible to have like an effective Hamiltonian.
For what?
In quantum chromodynamics.
Quantum chromodynamics. No, I can write the Hamiltonian at high energy. So here is the subtle point. So I will discuss we will discuss strong interactions. So what happens with strong interactions? They become weak and weaker when you go to higher and higher energies.
Oh, yeah.
And so there are kind of two regimes in the case of strong interactions. One is when you are at very short distances. When you probe short distances, the strong interactions become small, weak. So you can even develop a perturbation theory, and you can consider corrections, lowest order effects, and then corrections. Now, so what's going on with strong interactions? If you are just interested in these very short range interactions, you can do this. However, if you want to go to low energy physics, low energy, high energy interactions, then you are in this non-perturbative regime. So you go to lower energies, coupling of strong interactions effectively becomes very big, and so you cannot use perturbation theory.
Amazing.
So, highly relativistic neutron could decay from unique channel through beta decay.
Sorry, say again.
Can we observe beta decay through muonic channel?
Beta, why?
I think that we don't see it because of energy threshold. That
No,
neutron decays in.
No, so again, please avoid this confusion, because decay occurs in the rest frame. If you want, you can go always to rest frames. The process of decay is something which is Lorentz invariant, right? In a sense, of course, lifetime differs. But whatever you accelerate neutron up to any energy you want, it will still not decay with emission of mu. Because again, you need to consider decay in the rest frame. And then you have this 1.3 MeV, so you have lower energies release, and you cannot reduce mu. More questions? So, some of these questions, some problems which I gave, I haven't yet discussed, but that will be discussed already in the first two lectures next week. So you may start to solve things which you already can solve, but the rest, then you will know how to solve it. Like that. Okay, and for today, and then two other guys, who is you and with the second. Hey, yeah, so please come in 5 minutes. Give me 5 minutes. So everybody give the homework.